And just as in Oliver Goertz's talk, we'll talk about realizability, but we'll not talk about GKN graphs, but about realizability of equivariant chain complexes. And this is joint work with Henrik Ripping. And so I was a bit worried that this talk may be, just as the group is not connected as a space, the talk may be a bit disconnected to the other talks, but these groups are also elementary abelian, and the questions we'll consider are very elementary. So I hope the talk is accessible to everybody. All right, so for the whole talk, we'll fix, oh, I have opened the wrong slides, so give me a second. I should open these ones. Ah, okay. We'll talk about an elementary abelian P group of rank n, and the field will be F of characteristic P. And the motivation comes from a conjecture about the theory of transformation groups, a conjecture from the 80s of Carlsson. So he states that if you have a finite GCW complex and the G action is free, then the sum of its mod P Betti numbers, or more generally with coefficients in our field F, must be large, namely at least as large as the cohomology of a torus, namely 2 to the n. So n was the rank of our elementary abelian P group. And what is an example where we have such a free action? So we can think of C mod P as sitting inside the circle, and then a C mod P to the n as sitting inside the n torus. And of course, the homology of the n torus has dimension 2 times 2 times 2, exactly 2 to the n. So this is an example where we have such a free action, and we actually reach this bound. Now, when Carlsson was working on this, he focused mainly on the prime 2, and then thought, okay, maybe we can somehow work on this more algebraically. And there is an algebraic version of this conjecture, namely for chain complexes. So the condition that we should have a free action manifests now into the condition that we should have free modules, and the complex should be finite, means now that the chain complex should be bounded and finitely generated in each degree. And such a chain complex can have no homology, can have homology 0, so it can be acyclic. But if it's not acyclic, then the conjecture states that the dimension is again at least 2 to the n. So how does this algebraic conjecture compare to Carlsson's conjecture? If we take our GCW complex and look at its cellular chain complex, then we get exactly a bounded chain complex of finitely generated free modules, if we suppose that the action is free. And if we take a non-empty space, this chain complex will not be acyclic, it will have some homology, and then we can ask, okay, does this algebraic conjecture hold just for this chain complex that is given by the cellular chain complex of the CW complex? So this algebraic version is more general than Carlsson's conjecture. But more recently, namely in 2018, Marc Walker and Srikant Iyengar, they produced counterexamples to this algebraic conjecture. So there is the conjecture, the question if these counterexamples can be realized topologically, so that you could also produce counterexamples to Carlsson's conjecture. And the goal of this talk is to explain that this cannot be done, and also the methods that go into this. So if you want to do that, we first should see how these counterexamples look like, so we want to review them. And then I also want to explain what kind of tools there are to prove such a statement. And we see that the tools that exist don't work in this case, and we have to come up with a new one, and it will be a spectral sequence. And what I like about this spectral sequence is that it's very computable. And so we want to apply then this spectral sequence to the counterexamples. So let's look again at our group, and we will be interested in the group ring, and an easier description for us to work with is as a truncated polynomial ring. And to describe this isomorphism, I just have introduced here generators of the group, but we can forget about them afterwards again. So what happens if we take a polynomial variable xi, we send it to this ith generator minus the one of the group ring. And why is this actually well defined? So we work in characteristic p, means the p power of this is just this guy to the p minus 1 to the p, but the generator of the group to the p is just a neutral element, so it is the 1 in the group ring, and so we get here a 0. So this is a well-defined map. It's not so hard to see that it's surjective, and then for dimension reasons that it's an isomorphism. Okay. Now these counterexamples, they are constructed with the help of the Koszul complex. So what is the Koszul complex of this group ring? So it is a chain complex, but it also has a structure of a graded algebra. And as an algebra, it is just the exterior algebra of this ring on n generators that will denote by C1 to Cn. And it will be a differential graded algebra, which means that the differential is determined by what it does on the generators. And it just send the ith generator to this variable xi in the group ring. So let's look at this more concretely in the example where n is 2 and the prime is 2. And in fact, this will be our guiding example. We'll always look at n equals 2 and p equals 2. So what is then the Koszul complex? We start with our ring. Then we take the exterior algebra on it. So we have here the two generators, then their product. And what does the differential do? So it has to send this C1 to X1 and this C2 to X2. And then the differential on the product is determined by the Leibniz rule. So the differential of C1 smash C2 must be X1 times C2 plus X2 times C1. And so into the C1, we go with the X2, into the C2, we go with the X1. We can also already compute the homology of this Koszul complex. So here what happens, we just quotient out by this maximal ideal X1, X2, so we just get the field. Also here, what are the elements in the homology? So these are the elements that get killed by X2 and X1, and it's not so hard to see that this is a one-dimensional vector space spanned by X1 and X2. If you want to know what you have here, if you calculate the early characteristic up here, you'll see it's 0, so it must be down here 0 as well. So you know already that here it must be two-dimensional, and you can check that actually a basis for this vector space is given by X1, C1 and X2, C2. Okay, so what you would like to keep in mind is somehow this basis element for the second homology for later. But now in general, the homology of the Koszul complex is an exterior algebra over the field in n generators. I have written down the generators, but we will not need them. And in particular, so this is not a counterexample to the conjecture yet, because what is the dimension of an exterior algebra in n generators? It is exactly 2 to the n. So the dimension of this homology is not smaller yet than 2 to the n. But how can you maybe construct a counterexample out of this Koszul complex? So what Marc, Walker, and Srikant Iyengar did is they considered a cycle in the Koszul complex. And if you have a cycle, you can construct an endomorphism of this differential graded algebra just by multiplying with the cycle. And if you want to get the degree right, so you have to shift up the source by I. And then they took the mapping cone of this map. So this will produce our counterexamples, the cone of this map given by multiplication with a cycle. And in the counterexamples, the cycle is always in degree 2. So they give actually an explicit cycle, but for us, it will not matter that much how the cycle looks like. And the counterexamples are when n is at least 8 and the prime is odd. So then they find the counterexample to this algebraic version of Carlsson's conjecture, where the dimension is smaller than 2 to the n. And they raised the question, can now these counterexamples be realized topologically? And the answer with Henry grouping is that this is not possible. So what do I mean with being realized? You could think of by the cellular chain complex of a finite GCW complex, say up to quasi-isomorphism or homotopy equivalence, it's the same in this case. But we show that even a stronger result holds, that you can drop the finiteness assumption and it cannot be realized by any free G space. So we completely classify the mapping cones that can be realized, and they can be realized when W is a boundary or the degree is at most 1. And so let's go back to our guiding example to see how the mapping cone looks like in this case. So I said we would take the generator of this second homology group and look at its mapping cone. And if you take a mapping cone of a map between chain complexes, what you do is you take the 2 chain complexes and you shift one. And because we have now this double suspension, this one is actually shifted twice more. And so this is why it's 3 times higher. So you have the 2 Koszul complexes as before, but one is now shifted up. And here is the other one. And the map in between, this differential, is given by this element that we chose. So for our guiding example, what we want to think now is, how can we show that such a chain complex cannot be realized topologically? Okay, so what can we do? Maybe let's first think about this non-equivariantly. If you have a chain complex over a field, then it will be chain homotopy equivalent to its homology. And so it can just be realized by a wedge of spheres. Of course, we want that if the space has some points, then the homology is non-zero. So we want that H0 is not 0. But what this tells us is, a priori, you have no idea how you will realize this chain complex. Like there would be many options of spaces. I mean, you could say, okay, I want to take, if it comes from a space, let's say maybe look at the cochain complex, then we will have a cup product on cohomology. So there will be more structure. There will also be cohomology operations. But the problem is that here we have no idea how this structure should look like. And though there is some hope, namely Justin R. Smith has introduced an obstruction theory if you want to realize a free chain complex with a simply connected free G space. But in our cases, we have non-trivial H1, so we cannot model something with a simply connected space. And then the other point is, while I said we have no control over the ring structure in cohomology, there is a place where you actually have control, and this is in group cohomology. In group cohomology, how do you calculate group homology? Say you take a free resolution of the field by the group ring, and from every free resolution, you can define the cup product just algebraically, just from the free resolution. You don't need a space. And something similar happens if you don't look at your chain complex, but at the quotient when you quotient out by G. So suppose now your chain complex is realizable. It is chain homotopy equivalent to the chains on a free G space. Then its cohomology will just be the cohomology of the quotient space. And since the space is free, that's the equivariant cohomology of the space. So the Borel cohomology, the cohomology of the Borel construction. And the cohomology of the Borel construction is a module over the cohomology of BG. And it turns out that you can recover this action just algebraically from the chain complex. So this can be computed algebraically. But usually it doesn't give you enough information to say that a chain complex cannot be realized. But you can do more. You can also calculate the annihilator ideal in the group cohomology. So all elements in the group cohomology that kill the cohomology of the quotient space. And if this comes from a space, this annihilator ideal must be closed on the Steenrod operations. And this idea goes actually back that you look at such an annihilator ideal and the Steenrod operations to work of Carlsson and the work he did before he thought about this Torus rank conjecture. And it was related to the Steenrod problem. So there you ask, you take an equivalent module, you put in some dimension, and then you ask, oh, is there a space that is an equivalent Moore space, so whose homology gives you exactly that module concentrated in that degree. But if you do this calculation for our guiding example, then you'll see that this annihilator ideal actually is closed under Steenrod operations. And so you do not get any obstructions for realizing this mapping cone. Nevertheless, this example is instructive because it tells you what should you do. So you should somehow get some control over the ring structure, maybe not of the chain complex itself, but on the quotient. And moreover, you want to have some additional information, maybe some cohomology operations. And for us, this will be done with the help of the spectral sequence, where the cohomology operations come somehow from the differentials. And the spectral sequence is algebraically defined via filtration of powers with the augmentation ideal, and very easy to compute. Okay, so let's just realize that for convergence issues that the augmentation ideal is actually nilpotent. Namely, if we look the highest monomial that is possible, then we'll take x1 to the p-1 up to xn to the p-1. And this gives us the elf power. This is not 0 yet, but then if we take a higher power, then we'll get 0. So L plus 1 is the nilpotency index of our ideal. Now, if we have any co-chain complex of 3 right modules, then we can consider the spectral sequence obtained from filtration with powers of the augmentation ideal, though we'll go in the other direction with our index, such that we get an increasing filtration. So the bigger the k, the lower the power, so the bigger the chain complexes get, or co-chain complexes. And so now what we prove is that if this chain complex is realized by a space, if you're looking at co-chains on a free space X, then the spectral sequence is multiplicative. It will converge to the cohomology of the space X. And the one page has the following description. So its columns will basically be given by the cohomology of the quotient space. So the Q is the index that goes in the vertical direction, up and down. And then the index in the horizontal direction is determined by the degree of this monomial, where we put the y chase in degree 1. So this just looks like the truncated polynomial ring as before, like the group ring, but they have this y chase have actually a different meaning. Formally, it's what you obtain if you filter the ring of functions from G to F also with these powers, and then take the associated gradient. So maybe let's look at this in a picture. So again, if P is 2 and N is 2, then we have only one monomial of degree 0. We have here one time column given by the cohomology of the quotient. We have 2 monomials of degree 1. So we'll have 2 times the cohomology of the quotient, and we have 1 monomial of degree 2. So we have again 1 column given by the cohomology of the quotient. And then the spectral sequence has one more property. Namely, if we look at some cohomology class tensored with a yj, let's say one in here, and we want to know what is differential. So differentials will always go on the page one to the left and one up. So what we do is we take this cohomology class and then we cup it with element in H1 of the group cohomology to get one class, 1 degree higher in the cohomology. Okay. So maybe this is a good moment to have a break and ask if there are any questions.
How is the multiplication in your spectrals?
It seems that we lost contact with Marc. Marc?
Yes, I am back. I think it was my connection. I'm sorry.
Right. Okay.
Okay, I'll continue.
Yeah.
Okay, so were there any questions?
How's the multiplication in your spectral sequence looks like?
Yes, so here, let me say here. So in one direction, you have the multiplication you have from the cut product in the cohomology ring, and in the other direction, you have this truncated polynomial ring. So you multiply the elements in the group cohomology together and the ones in the truncated polynomial. Okay.
Thank you.
So the differential looks like a homology spectral sequence rather than a cohomology spectral sequence.
So there is something to say about differential, namely we don't do one reindexing conventions where in the filtration you would somehow then in the quotients add two numbers to the filtration degree. And so the differentials will look a bit different. And also the convergence will be horizontally and not on the diagonal. Okay. But so what's also different is the way we use the spectral sequence, both in what the aim is and what the difficulties are. So usually if you look at the spectral sequence, maybe you want to say something about what the spectral sequence converges to, or you want to say something about the E2 page or E1 page from what it converges to. And we want to use all the geometric information, the multiplicative structure to make the computation easier. And what's here happening is it's very different, that the computation just algebraically is very easy. This is not a problem, but what we want to do is then find contradictions to the multiplicative structure. So this is the strategy to show that some co-chain complex cannot be realized topologically. So what we have to do is we have to calculate the spectral sequence algebraically, just from the definition. And because if it came from a space, we would have this action of H1. This will tell us something about the multiplicative structure in the spectral sequence. And using this information, we will find contradictions to the Leibniz rule. And I think this is maybe not the usual way we use spectral sequence, so it's helpful if we show this as an example. So let's look again at our standard guiding example. So the chain complex that we were looking at was the following, and it's actually dual, so the co-chain complex looks the same. So this is again an n is 2 and p is 2. So in this case, the group ring is just given by generated by two variables, and we quotient out by x1 squared, x2 squared. The ideal will be x1, x2, and I squared will be generated by x1 times x2, and I to the third is 0. And then if you look at the definition of the spectral sequence, what you have is you have this quotients of the filtration. And the first filtration quotient that we have is here, this C star multiplied with I2. Okay, this one is 0. Then the next one is I modulo I squared. And then we have the whole chain complex divided by C star I. Okay. Then in the example, how does this look like? Let's focus on this guy first. So what we have to do is we have to take this quotient. So for each FG, we have to quotient out I, which means just the field stays. So for each FG, we get one copy of the field. And what is the generator of this vector space? This is just the neutral element of the group. And also note that the differentials, they're always in I. So if we take then cohomology, it doesn't change anything because the differential is 0. A similar thing happens here, but now the quotient of I modulo I squared is two-dimensional, generated by x1 and x2. So for each FG, we get two copies of F, one indexed by or with basis x1 and one with basis x2. And I squared is a two-dimensional vector space. We get again, it's a one-dimensional vector space with basis x1, x2, and we get for each FG again one F. So this is how we set up the E1 page, just algebraically from the definition. Now we'll have to compute differentials. And now this is a pity that I don't have my other slides. I should have checked that before. So now we have a lot of information, but let's try somehow to go through that step by step. Okay, so you want to calculate some differentials. Let me skip how you do that for the D1 differential. Just what's here is the rank of these differentials. What is an important differential is the one on the E2 page, on the second page. So I claim that this differential here is the identity. So why is that? So if you look at our generator here, the neutral element, and you want to calculate its differential, then it's induced by the differential that is here in the chain complex. So we have to multiply it with x1, x2. But if you multiply this guy with x1, x2, we get exactly the generator over here. So we get this one. And so this is why this is an isomorphism. Now I said that if the cochain complex is realizable, then you have a multiplicative structure. And I claim that the generator here will be the product of two generators from here. But this will contradict the Leibniz rule. Namely, if we have the two generators here and they multiply to give you this guy here, and the differential of this one is non-zero, then by the Leibniz rule, it must be the differential of the first guy times the second guy, plus minus the second guy, the first guy times differential of the second guy. And because the differentials here arrive to the left, so there will be 0, this must be 0, and we get the contradiction. So now you will probably ask me, okay, you see, if you take two guys in here, you multiply, you need to end up here. But the question is, oh, why should this be not the 0 element? And this is because we also have control over some part of the multiplicative structure. Okay. So let me explain that. So this is what happens in the second step of the strategy. But if you want to do that, first we need somehow to identify the descriptions of the E1 pages. So when you look at it geometrically or topologically, then the E1 page had somehow indices yi's, but now we have these indices xi's, and we have to be able to go from one description to the other. And if you go through the isomorphisms, then what you'll see is that the monomial in the xi's corresponds to the monomial in the y-ice, but what happens is that the powers, they change. Namely, you have to replace the index by what you have to add to reach p-1. So what is more important, how this looks like in our example. In our example, this means that if we had the x1, x2, we don't have this one anymore, but expressed through the y-ice, we will have a 1. The x1 corresponds to the y2, the x2 corresponds to the y1, and the e corresponds to y1, y2. And now recall that in the geometric description, the D1 differential is given on a yi by multiplying with an ai. So ai was a cohomology class of the group ring in dimension 1. And so let's see what is the differential of this y2. So in the algebraic description, this is just the x1. It sits in here. We need to calculate its differential. So for the first coordinate, we will multiply with x2. We get this one here, x1, x2. But in the second coordinate, we'll get x1 squared. We get 0. So this is the element like 1, 0 in this two-dimensional vector space, which means it is the first generator of this two-dimensional vector space. And similarly, the A1 is the second generator. And now we can go on. If you want to know what is A2 times A1, then we can go over there. We have the A2Y1 in there. We calculate this differential algebraically. What we realize is that it gives you exactly the generator here, but by the geometric formula, if you look at A2Y1 and we calculate its differential, then it must be just A1, A2. So what we obtain here is actually this A1, A2, and we see that A1, A2 is not 0. Then here we have the same column, so we also need to have A1, A2. I just add the Y1, Y2 to indicate that we are in the column over here. And then what we are missing is what are actually the two generators here that survive. And if you go through the calculation, then you'll see that the two generators correspond exactly to A2Y2 and A1Y1. And so we first still have these two generators here. And we see that if you multiply, we get exactly this one. This is the product of these two. And this means that as we claim the generator here is the product of these two generators, and we'll get our contradiction to the Leibniz rule. Okay, are there any more questions? Okay, so this is how in an example you can show that this chain complex is not realizable. And in fact, the strategy works for all the family of mapping combs that we're considering. It's just that the combinatorics, they become more involved. So what we show in this way is that all these mapping combs cannot be realized if the cohomology class has degree at bigger than 2, or if it's not a boundary, or no, if it's non-trivial and the degree is at least 2. So, but how can we realize them just for completeness if this W is a boundary, so it represents 0 in homology, or if the degree is at most 1? So first, if it's a boundary, so if it represents 0 in homology, then the mapping cone just looks like 2 times the Koszul complex just shifted. And the Koszul complex can be realized geometrically by the n-Torus, and the shift you obtain if you cross it with a I+1 sphere. Now, if your W represents a non-zero homology class of degree 0, then the mapping cone will be contractible, so the homology will be 0, and you can realize it by the empty space. And then the example that is the most interesting one is when your W is non-zero and of degree 1. then you can realize it by S3 cross an n-1 torus. So to describe the group action, this is the easiest way to do that is to look at the example where W is just the generator of the Koszul homology, or one of the generators. Then you can act on with one of the CMOD P's on S3 by looking at S3 inside C2, and you just multiply diagonally on the two coordinates. And with the other CMOD P to the n-1, you act on the torus by rotating coordinate-wise. But if you want to have a general element in the first Koszul homology, then you'll have to change this group action. You have to pull it back along a group automorphism. And for that, we had to introduce an action on the Koszul homology. Okay. So what are questions that remain? So a few weeks ago, I went to another online conference where Marc Walker talked about joint work with Erika Hopkins and Alexandra Cecilianu. And they asked now the following question. Okay, we know that the dimension of the homology can be smaller than 2 to the n. We have counterexample to this algebraic version of Carlsson's conjecture. But does it hold asymptotically if n goes to infinity? Then a question that I'm interested in is also related to that is, okay, 2 to the n is not a bound that holds, but what is the best bound that actually holds? And I mentioned that their counterexamples are when the prime is odd. So what happens in characteristic 2? This is open. And then related to the spectral sequence, we know, or we have actually constructed the spectral sequence more generally, not just for elementary abelian P groups, but for any finite P group. And there we don't have the group theoretical interpretation of this D1 differential. So this is another question. And then the last question is about what I mentioned for the realizability of these chain complexes, that in the last case for W's of degree 1, we had to introduce an action on Koszul homology. For that, we have started talking to Srikant Iyengar because it would be interesting to extend it to other rings. We can do this now for complete intersections, but we don't know if this works for local rings in general. So I hope that these questions about elementary abelian P groups were elementary enough to be interesting, and I thank you for your attention.
Thank you, Marc. Shall we unmute the mic and thank the speaker?